Welcome to this talk on my latest research. Today we'll be looking at how internal oscillatory waves shoal and how the behaviour is dependent on the background stratification. This is work I've been carrying out as part of my PhD research at Newcastle University with my supervisor Magda, and we've also been working with Marek at University of Waterloo and with Davies at University of Dundee. Internal oscillatory waves are found commonly in geophysical stratified fluids, and they're an important part of the cascade of energy from global scales of mechanical energy input like the tides and wind down to dissipation at molecular scales. Because they're non-dispersive, they're able to travel long distances without change of form, but as they travel over changing topography, such as shoaling on a slope, then they are able to dissipate large amounts of energy and cause high amounts of mixing. They're also important in these environments for sediment transport and resuspension, as shown here, where we have under each wave in the train of internal oscillatory waves a peak in the backscatter as sediment is resuspended underneath. They're also important biologically, as they're able to bring about mixing of deep waters, which are often nutrient rich and much cooler, to benthic ecosystems. Shoaling internal oscillatory waves have been studied fairly well in the past, particularly by the three studies indicated here, which have together produced a classification system consisting of 4 different types of shoaling behaviour. First of these is fission, and there's also surging, collapsing and plunging, and these have been delineated based on this figure here, where we have plotted wave steepness against slope. So the first of these types of breaker is the surging breaker. This is found where we have small wave amplitudes, and it results in a small wave propagating up the slope and producing a surging bolus which continues upslope. Next up is the collapsing breaker. This is found in the mid region of the figure, so we have some intermediate values of slope and wave steepnesses, and this is characterized by the boundary layer effect of the separation bubble, which grows in strength as it shoals and causes the PIC incline to be drawn back on itself and to collapse. So this is what we see here. The drawdown of the fluid causes the boundary layer to form a separation bubble, and this causes global instability related to the vortex. And again, that fluid from the deeper layer moves upslope, but there's a lot more mixing involved this time. Then we have the plunging breaker, which is found at high wave steepnesses and slopes. Here is where we have overturning related to the rear of the wave at the top, overtaking the trough of the wave. So you see this happening here, and now we get plunging forward of this lower layer fluid, which produces Rayleigh-Taylor instabilities. We then have fission breakers as well, but since these don't seem to change much in different stratifications, we won't be talking about them very much here. So we have been investigating these in the laboratory and also in numerical model spins, which happened once lockdown started and our access to the lab wasn't possible. The spectral parallel incompressible Navier-Stokes equation solver was developed at the University of Waterloo in 2013 and uses spectral methods on parallel threads to solve the Navier-Stokes equations. These are in order here, from the momentum equation, the continuity equation, and conservation of a tracer. We've previously seen that this model is very good at replicating laboratory scale flows, so it seemed very appropriate for us to move into this when we were unable to continue in the laboratory. And additionally, it has the advantage that we can see other wave properties such as the density and the vorticity much easier. So to look at this, we have our internal wave tank set up, 7 meters long, and at one end we have a gate. So in the main tank we have lower layer of fluid which is more dense, and above it is an upper layer. In this case, the upper layer is linearly stratified with depth, and behind the gate we have an additional volume of fluid added to the top, which has the same density as the fluid at the surface of the main tank. This causes the picnic line to be displaced behind the gate, so that when the gate is removed or the simulation is started, there is an internal oscillatory wave propagates from right to left. On the far side of the tank is the slope, which we vary in steepness, and where necessary we can extend the length of the numerical tank to extend our slope steepnesses. So in the numerics, this is what this looks like, where we have a picnic line extending through the top half of the water column throughout the main tank, and then in the gate region it's displaced, and there's a small transition distance where in the numerics we don't have a gate. Most of these studies so far that we've outlined, which we used to produce this classification, have all used the same stratification. This consists of a fairly thin upper layer, which is homogeneous, separated from a further lower homogeneous layer by a thin picnic line. And this is similar to what we see in certain parts of the ocean, like the Labrador Sea and the South Atlantic. However, stratification in the ocean does change quite a lot, and this is spatially and also seasonally, and this can be characterised by the picnic line thickness and the picnic line depth on a tank profile. So we see in the East China Sea a kind of extreme of this, where the picnic line extends throughout the entire water column, and we thought it would be good to explore a few of these different stratifications. So we started with the three-layer stratification, similar to what's been used in past studies, to bring about validation of past results against our own model and experiments. We then moved into what we're calling here as two-layer stratification, where the picnic line has been extended throughout the entire top layer of the water column, and we lose that homogeneous top layer. Finally, we extend the stratification even further with a higher value of the picnic line thickness, so that the picnic line extends throughout the entire water column. Here we're calling this the linear stratification. So our results, we have found in the three-layer stratification that our results are in strong agreement with past literature. This figure shows with the crosses the past literature's results, whilst ours are shown in the filled circles. It's found that for each of the regimes that we'd expect to see based on the slope and wave slope steepnesses parameters, that the categories are correct as we'd expect them. However, moving to the two-layer stratification, we lose the ability to form plunging breakers. Instead, the collapsing breaker is formed across both of those two regimes. We believe this is because having a density gradient throughout the entire top part of the water column suppresses the ability to form plunging dynamics, which form at the picnic line. So, looking at a wave with the same wave steepness and over the same slope as we had the three-layer plunging case before, in the two-layer stratification, you'll see now that we form a collapsing breaker with that characteristic separation bubble forming and causing the picnic line to be drawn back and collapse on itself. So now we have lost the plunging dynamics because we have a density gradient in the upper layer. What happens when we remove the density gradient throughout the entire water column, including the bottom gradient where we form these collapsing dynamics? Well, in the linear stratification, we now also lose the collapsing dynamics because of the density gradient at the lower boundary. Instead, we form surging breakers across that entire upper space of the diagram, and the only other form of breaker is the fission breakers. Looking at this at a low wave steepness, we see the isopycnals spread nicely, and then they steepen as the wave comes in, as the non-linearity coefficient changes, and a bolus is formed propagating up the slope. However, in this linear case, now that we have the surging type breakers found across this whole range of wave steepnesses, we find that some of them become unstable when the bolus forms, and Kelvin-Helmholtz instabilities are able to be formed on the upper surface. So, looking at this, we have again the same wave steepness and slope steepness as we showed earlier for the plunging and the collapsing forms. The wave comes in and the isopycnals steepen, but as the bolus forms, we get instabilities on the upper surface of it, which form in a train of 4 or 5 Kelvin-Helmholtz instabilities. This is a feature which will cause a lot of mixing compared to the surging breakers we saw in 3-layer stratification, or even the same surges we saw in the same stratification at lower wave steepnesses. So it seems that the stratification really matters when we're looking at these studies of shoaling internal solitary waves, and in particular the location of the boundary in relation to the dynamics that we're looking at seeing. So we can't form plunging dynamics where there is a density gradient across the upper surface. Likewise, we can't form collapsing breakers where we have a density gradient at the lower boundary. And finally, it's interesting to note that as we now have surging breakers in a regime that we wouldn't have found it in the other stratifications, this changes the dynamics again so that we can form instabilities on the boluses, inducing a lot of mixing. Thank you for coming to the talk, and I hope you enjoyed it. I look forward to seeing you at the VEG talk on the 26th of April.